Hey all listeners, this is Pradesh Aurya Quantum Guru. In this video, I am going to present you how to deal with the problem solving angular momentum of a rigid body involving multiple angular velocities, like this question of IIT-JEE 2016. If there is one question that might be pinching you for your JEE Advanced preparation, that is this question. JEE Advanced is just a few days away, so it is important to understand what are the real concepts that are used. Unfortunately, the concept that is taught at IIT-JEE level are insufficient to deal such problems, and the internet is flooded with the insufficient tool to solve this problem, and no doubt most of them are incorrect. So please go through the whole video. This video is going to be long, and first I'll develop the necessary tool how to tackle such problem, and then I'll proceed to solve this question. And the solution given by JEE is also not correct, because they had given two set of answer. One was A and B, or one only A, so that is not possible. And the answer that will come, that is not important, because that will be very not very good value. So basically we have to understand how to solve such type of questions. So let's go ahead with the angular momentum itself. So let me revisit what is angular momentum and CTRM, combined translation and rotation of a rigid body about a point. So suppose this is a rolling cone. This is cone is on a lying on a surface and it is rolling. It can have multiple angular velocities. So like this, its axis, about this axis, it is rolling like that, and this whole thing is center mass is moving like that. And there can be other cases also, so that is not important. So this body has a net angular velocity and it has a center mass. Total mass is m. We want to find the angular momentum about point O. The point O could be anywhere inside the body, outside the body, at the center mass, anywhere. So with respect to center mass, at this moment, the position vector of center mass is RCM. Velocity of the center mass is VCM. Mass of the body is m. So angular momentum of this whole body about O is given as L about O is m RCM cross VCM plus summation of mi RICM cross VICM. So what is this thing? This term is as if we put the whole mass at the center of mass. So like we define the angular momentum of a particle about a point. So if we put the whole mass at the center of mass, and that center mass is obviously moving with the velocity of center mass, then that is that momentum about O. So this is known as the angular momentum of center of mass with respect to O. That is not right to say, but having said that, that is real meaning is that if you put the whole mass at the center mass, then that term represents the angular momentum of center mass about O. And what is this term? This I is a general ith particle, RICM is the position vector of that particle with respect to center mass, and VICM is the velocity of that ith particle with respect to center mass. So mi RICM cross VICM is the angular momentum of the ith particle with respect to center mass. So their summation will give the total angular momentum with respect to center mass. So this term is the angular momentum of center mass about O, and this term is the angular momentum about center mass, and we call this term as a orbital angular momentum, and this term as a spin angular momentum. And the real problem comes here, because at IIT-JEE level, that is just taught to write that ICM omega, and that is true in some cases, in the basically at the most of the cases where there is a only one angular velocity, but not so in the case of a multiple angular velocity. So the real problem is understanding this term. So we'll proceed to derive this term. In general, basically this is angular momentum about center mass, and center mass is just a point. So basically we will derive angular momentum of a rigid body about a general point involving multiple angular velocity, and deriving so we will come across many other terms that are called inertia tensor, and that will be tools for dealing such type of questions. So now in general, let's go ahead for the angular momentum of a rigid body involving multiple angular velocities about a point O. That's what we want to find. So suppose this is a rigid body. It's kind of a top, a spinning top, and this spinning top is rotating about its axis, and this center mass is also moving like that. So it has a two angular velocity. This is a one angular velocity, and that is another angular velocity, and the resultant angular velocity is a vector. So when we call the resultant angular velocity, that is the vector sum of all these omegas. And suppose the net angular velocity is the omega vector. And let's take one general point of the body. Suppose this is the general point of a body. Its mass is dm. Position vector with respect to O is the point about which we wish to find the angular momentum. So position vector of dm with respect to O is r vector, and the velocity of this particle is v. So angular momentum of this dm mass with respect to O, that is just a particle point. So that is a dm r cross v. And the position vector of this r is, say, xi cap plus yj cap plus zk cap, and the velocity angular velocity vector, the net angular velocity vector, that is the angular velocity is a vector, so it will also have component. So that component is, suppose, omega xi cap plus omega yj cap plus omega zk cap, and add them to get net angular velocity omega. So we know that from the rotational motion that the velocity in vector form, velocity of this point, we can write omega cross r. That is omega this, and this is r. So, and angular momentum about O, that is r cross dp, and dp is the linear momentum of this particle, and dp is equal to dm into v. So that will be r cross dmv. Dm I'll take outside, so dm r cross v. R is this, and v I will write omega cross r. And now I will put all the first, before I will use this cross product rule. The cross product rule is vector triple product, that is a cross b cross c is a dot c b vector minus a dot b c vector. So just using this thing, we will get r dot r omega minus r dot omega r vector, and dm is outside. And this r dot r will become simply x square plus y square plus z square, and omega I'll write with component, and r dot omega will become x omega x plus y omega y plus z omega z, like this. And this I've written, and r vector, and then in the next page I will simplify this thing. So that was the whole thing. You can recheck all those things. So if we simplify this thing and term by term, so first of all dm is outside, and this whole thing is here. So I'm simplifying this thing. So I'm taking x square plus y square plus z square into omega x minus I'm recollecting the terms of I cap, j cap, and z cap. So we'll get like this thing. So this is how I have simplified. And again simplifying in a more precise manner. So this is a dm x square plus y square plus z square omega x. All the omega x square term I am clubbing together. So here x square and this x square will get cancelled. So I will get y square plus z square omega x minus xy omega y minus xz minus xz. This is xz omega z I cap, and similarly the other terms. So this is what we get. If I integrate this whole thing, I will get the total angular momentum about O. So that was angular momentum of the dm mass about O, and rewriting this, and if I integrate that whole thing, so I will get the total angular momentum of the body about O. Okay, and now just I want to write the O. Angular momentum is also a vector, so L about O is the x component I cap, Lx I cap plus Ly j cap plus Lz k cap, Lx is the x component of angular momentum, Ly is the y component, and Lz is the z component. So separating x component, y component, z component of the angular momentum. So this term is basically Lx, and this term is Ly, and this term is Lz. So Lx is the integration, now dm, integration dm I am taking inside. So Lx is the integration of y square plus z square dm omega x, and other term is this and this. Similarly, Ly, Lz, Lz can be written. So this looks very cumbersome, so I want to give some name. So this I want to give some name, say Ixx. This integration I want to give a name Ixy, and this Ixz. Similarly, this Iyx, this Iyz, this this Iyy, this Iyz, this Izx, Izy, and Izz, like this. And I will rewrite them again. So just writing this way, now that will become simpler. So Lx will become Ixx omega x plus Ixy omega y plus Ixz omega z. Ly will be Iyx omega x plus Iyy omega y plus Iyz omega z. And Lz would be Izx omega x plus Izy omega y plus Izz omega z. So that whole thing can be written here. And just looking at, you can realize that can be written as in terms of matrix multiplication. So I can write this in terms of matrix multiplication. This is a angular momentum matrix Lx, Ly, Lz, and this is 1 cross 3 matrix, and this matrix has 9 components, Ixx to Izz, and this is a 3 cross 3 matrix, and this matrix is known as the inertia tensor, and this is the angular momentum matrix omega x, omega y, omega z. So this is a very compact way to write, right? So now this whole thing can be written as a singular notation, and this we can write L vector is equal to that, this matrix is known as the inertia tensor, so that is I, inertia tensor I, and that is the angular velocity. And this I is what? I is this inertia tensor, which has 9 components. Any physical quantity which has 9 components, 16 components like that are called tensor. A quantity which has 3 component is a vector. A quantity has just 1 component, that is a scalar. So in general, all quantities are tensor. Vector is a tensor of rank 1, scalar is a tensor of rank 0. So because this thing involves 9 components, so that's why we call it inertia tensor. And what is I? Here I is called the inertia tensor. This is moment of inertia of body about O. Remember, you are taught in 11th that I is the moment of inertia about axis. No, this is the moment of inertia not about axis. This is moment of inertia about a point, and that's what we have to understand. And one more thing, that this L is not in general in direction of omega. Like that can be possible, See, omega is omega x I cap plus omega y j cap plus omega z k cap. So that can be possible if all Ix, X, Iy, Iyz are equal, then that could be possible. That may not be possible. So L is not in general in direction of omega. That is one important thing. So now we want to give interpretation of these terms. There are 9 terms. So L is angular momentum about O, omega is the net angular velocity, and this I is the angular momentum, I is the moment of inertia of the body about O. So once again this thing, and we had replaced Ixx, Iyy and so on in place of these integrals. So Ix is this, Iyy is this, Iz is this, and so are this. So these 3 terms, these are the diagonal terms. Ixx, Ix, Iyy and Izz, these are the diagonal terms, and these are the off diagonal term, and this is a symmetric matrix. You can see that Ixy and Iyx are same, Ixz and Izx are same, and Iyz and Izy are same. So these are the diagonal elements and these are off diagonal elements. By suitable transformation, the off diagonal terms can be made to 0. Let's see how. First of all, let's try to get their interpretation. So interpretation of the first diagonal term, that is the Ixx. So suppose this is our coordinate system xyz, and this is a point xyz, and there is a point dm here. So this height is y and this is z. So if I want to find the distance of dm from x-axis, so from here you can say that this is a y, this is z, and that is the distance of dm from x-axis. So distance of dm from x-axis, dm basically a point whose coordinates are x, y, z. So this distance is the square root of y square plus x square z square. So Ixx was this, and this is Rx, and Rx is what? The distance of dm from x-axis. So distance of dm from x-axis, so I can write this integration of Rx square dm, and that is a famous thing. This is nothing but moment of inertia about x-axis. If dm is a point mass and that is separated at a distance Rx from the x-axis, so integration of Rx square dm is the moment of inertia about the x-axis. So this term Ixx is nothing but the moment of inertia, proper moment of inertia that we use is about x-axis. So similarly, Iyy is integration of z square plus x square dm should be the moment of inertia about y-axis. Izz integration of x square plus y square dm is the moment of inertia about z-axis. Alright. Now comes the term product of inertia. So these are the called, because those terms are multiplied, so these are called product of inertia. Ixy, Iyz, that is the integration of minus xy dm, and similarly these terms. So what is the interpretation of the product of inertia term? So let's see. We'll see that product of inertia terms are a measure of the asymmetry from the with respect to the corresponding axis, like this. So suppose we have, this is a disk, circular disk, uniform mass density, and I've chosen two coordinate axes, x-axis and y-axis. I wish to find Ixx and Iyy, both are same, Ixx and Iyx. So this y-axis passes through center, and x-axis is perpendicular to y, that's it, and that can be anywhere. So if I take two pair of points on this, like I am taking dm here and dm here. So this x naught y naught, and its coordinate is minus x naught y naught. So we can divide this whole body into such pair of points, because this body is symmetric about y-axis, so we will always have two such pairs. So if I get, for this point I get xy dm, so that was x naught y naught dm, and for this point xy dm would be minus x naught y naught dm, and their sum would be 0. So this whole body can be divided into such pair, their sum is 0. So overall Ixy Iyx, that is a minus of integration of xy dm, for the whole body this integral is 0. So this integral is 0. Similarly here, now this body is symmetric about x-axis, and y-axis could be anywhere, just the thing is that they are perpendicular to each other. Again I can get a pair of such points, like this point coordinate has a x naught y naught, and this coordinate is x naught minus y naught, and we place mass dm here. So here integral minus xy dy dm. So for this thing x naught y naught dm, and there is a product would be minus x naught y naught dm, so that sum would be 0. So dividing this whole body by such pairs, the whole integration will be 0. So if this integral is 0 on this body, on 0 this body, this was symmetric about only y-axis, this was symmetric about only x-axis, and if it is symmetric about both and xy axis, so obviously that integral will also be 0. So in a way, if the body is symmetric about any of the two axes, so that product of inertia term is going to be 0, and by choosing our coordinate system in such a way that body is symmetric about either of these axes, so we can make the product of inertia term 0. And if the product of inertia is term 0, the 9 terms of the inertia tensor will be reduced to just 3 terms, and that's what we want. So we can say that if x and y are the two x perpendicular axes, then if ix and ixy or iyx is 0, if first of all mass distribution should be uniform, and one of them, one of the x axis or one of the y axis or even both should be symmetric axis of the body. And by choosing our coordinate system such a way, we can make the product of inertia term 0. So by a suitable choice of coordinate system, coordinate axis, the product of inertia term can be eliminated. Then suppose if I choose our coordinate system as a x-axis, y-axis, z-axis, not necessarily same as your x, y, z-axis. I have chosen my new x, y, z-axis, and by those axes, by those choice, I have made product of inertia term 0, and then these main x, y, z axis would be called principal axis. So principal axis, then inertia tensor will become only these diagonal terms. The off diagonal term has 0. That has made a thing quite simpler. And then we had this L vector was inertia tensor into the omega vector. So if I write this Lx, Ly, Lz, that is the Ixx, Iyy, Iz, other term 0, that is omega x, omega y, omega z. Just do the matrix multiplication. So we will get Lx is equal to Ixx omega x, Ly is Iyy omega y, Lz is Izz omega z. So first of all, getting three components of the angular momentum along principal axis and then clubbing together. Like net angular momentum would be Lx I cap plus Ly j cap plus Lz k cap. We will get the overall angular momentum about the required point. So now we have got necessary tool of using the angular momentum, but I will just illustrate it how this logic is also used for our normal case that is taught at the JEE level. So here this is a rolling body on this plane that is rolling. You can, for the understanding thing, this is a disk. The center of mass has a velocity vcm and it is rotating with angular velocity omega. It is just moving forward and it is rotating like that. So in the direction of the rotation, just curl the hand of the right hand. So this is the omega vector. So omega vector, along the omega vector, I am assuming that is our x-axis, and this is a y-axis and this is z-axis. So clearly x, y, z are the principal axis, because about axis, y-axis, z-axis, body is symmetric. About any of these axes, body is symmetric. So these are our principal axis. So principal axis. So now omega x along the principal axis x, that is omega, and there is only one omega. So omega x is just omega, omega y is 0, and omega z is also 0. And we are talking about only the orbital spin part of the angular momentum. So spin part of the angular momentum, LCM, that is the angular momentum over the center mass, and that is Lxx I cap plus Lyy j cap plus Lzz k cap. And Lxx I cap would be Ix omega x, that is simply Ix omega, and Lyy would be 0 because there is no omega y. Similarly, Lzz is also 0 because omega z is 0, and we simply used to write this Lxx as a ICM omega. What is ICM omega? ICM is the moment of inertia about center mass along the angular velocity vector. So inherently this angular momentum comes in the direction of omega. But if there are other omegas also present, so L will not come in the direction of omega, and that's what comes in the case of the body having multiple angular velocities. So now here comes the JEE Advanced 2016 question. So let me reread the question. This is a assembly having two thin circular discs of mass m and 4m, and they are separated by a rod through their centers. The L is root 24a, and if I extend this rod, that will go to the ground point O, and that length is also L, and this is L, and this is rolling without slipping. Okay, this is rolling without slipping. The whole assembly angular momentum at point O is L. So when we talk about the overall angular momentum, that includes the orbital and spin part both. So now which of the following statement are true, and we'll see each option one by one. Only one option is correct, rest are not correct, because this is a complex question and they forgot that in JEE level that is not allowed. So but I will present the true solution. Okay. So first part was the simple. The center of mass of the assembly rotates about the z-axis with angular velocity omega. So this whole assembly is rotating about this axis, and that angular velocity is omega, and that is kind of a spin angular velocity, and the center mass is moving like that. So this angular velocity omega is, if you make a direction, so this direction is along this, and that is a spin angular velocity. L was given, okay, first of all let's do the geometry part. This L is root 24, and this is A, and this was given 5a. So sine theta cos theta, sine theta would be A by 5a 1 by 5, and cos theta would be L by 5a, that is a root 24 by a 5. So sine theta cos theta I've written. And now this spin angular velocity like this, what is rotating, so that will be in this direction, and I'll use the concept of IUR, instantaneous axis of rotation. There are three ways to look at an IUR. The best way, if we have IUR, is a kind of a fixed axis at that moment. All the points of the fixed axis have no velocity. So if it is rolling without slipping, so this point is in contact with the ground, so it should have a zero velocity. So similarly, this should have zero velocity. So IUR must pass through these 2 points, so that will be along this line. And along IUR, there is a net angular velocity is along IUR. So IUR is along this direction. I will tell that thing later. So this IUR, and that is net angular velocity. And if we look the center of mass, see here most of the solutions that are available in the net are wrong. Just you imagine yourself, suppose this is center of mass, and will center mass be always at the same height from ground or not? Obviously it will always be at the same height from the ground. So just look the trajectory of the center mass. So center mass will move in a horizontal circle like that, and so there is an orbital angular velocity of the center of mass, and that is this omega O, and that is along the z direction. And net angular velocity is obviously the vector sum of the any other angular velocity. So it has a two angular velocity. One is the spin angular velocity, and the center mass of the assembly is rotating like this in a horizontal circle. So omega net is the vector sum of these two. So, and this theta, so this is theta. If I make a component of omega s along this direction, that will be omega s, and omega is basically omega, and omega O is basically omega z. So if I make a component of omega z, so this component would be omega s is omega, so that component will be omega cos theta, and that component will be omega sin theta. So omega sin theta, because net omega is here, so along this direction all the components should vanish. So this omega sin theta will be equal to omega naught or omega z. So omega naught is equal to omega sin theta, and basically this component of the omega s is the omega net only. So omega net is omega cos theta, and omega s was omega, and sin theta is 1 by 5. So omega z is omega by 5, and that is the only correct option, that is we got immediately. And we'll use now later omega net. So omega net is basically omega s cos theta. So omega s cos theta mean omega cos theta, and cos theta is root 24 by 5, so that is omega root 24 by 5. All right, so first part is done, dusted immediately, very easily. And now we want to find the magnitude of angular momentum of the center mass of the assembly about the point O. So for that thing we need to locate the center mass. So suppose center mass is obviously somewhere here. This center mass, suppose center mass is at a distance of RCM from O. And for this thing I can put the whole mass m at the center mass of this disk and 4m at the center mass of this disk. So RCM would be m into L plus 4m into 2L divided by m plus 4m. So put that thing, we'll get 9m by 9 ml by 5, and L is root 24 by 4. So that would be 9 root 24 A by 5. All right. So the center mass is located, and now the velocity of center mass we want to find out. So all this thing L was given, RCM we have located, and see, this is IOR. This is IOR, and I am assuming this to be x-axis. And IOR is the axis about which motion is the pure rotational. So this is the IOR, and if we get IOR or the fixed axis, so any point that is at a distance x or distance say r from IOR, its velocity would be r into omega net. So this is the center mass, and the center mass is say if the distance y above the x-axis. So simply the velocity of the center mass would be y into omega net. Simple as that. Here also many solutions that are wrong. So center mass, and obviously, so this velocity would be the into the plane. So that is coming to be, if this is my x-axis, this is my z-axis. So velocity of the center mass will come in the y direction. And the simple way is just get this y, and omega net is known, so that is y, and y would be nothing but 2L sine theta. That is one way. So I am also presenting a way in which directly it will come in terms of the vector form. So also I can write velocity of any point of the rigid body is the r omega cross r. So the position vector of this velocity of center mass is, I'll tell that. This is the position vector of the center mass, that is omega cm, RCM, and the omega net in the direction. Omega net has a magnitude omega cos theta, and direction is minus I cap. So omega net is omega cos theta minus I cap. And position vector of center mass is basically, this is, I can make a component. This component would be 2L or r sine theta, RCM. This is not 2L basically, this is L plus that was 9L by 5, something like that. So this position vector would be RCM cos theta I cap plus RCM sine theta k cap, and omega net is this. So if I make a cross product, this I cap cross I cap term will vanish, and the other term would be this, and that is coming to be along j cap direction. That would nothing but simply omega net into that height y. So you will get this thing, and put the sine theta cos theta and RCM value. So VCM we will get, VCM we are going to get 216 by 125 omega a j cap, and that is into the plane. Now that we have got the VCM, we can simply get the angular momentum about O of the center mass. So magnitude of angular momentum of the center mass about the point O. Okay, fine. So clearly this velocity is here, so that the angular momentum of the center mass, if I put the whole mass at the center mass, it is 5m. So angular momentum what over the 5m RCM cross VCM, and this is going to be the perpendicular to the plane of RCM across VCM, and that should be something like that. So and this is again x-axis. So and that angular momentum also known as the orbital angular momentum. So orbital angular momentum is L center mass, angular momentum of the center mass about O. There is a 5m RCM cross VCM, RCM I will write again in the vector form, and VCM also in the vector form. So RCM vector form is RCM cos theta I cap plus sin theta k cap, and this is a VCM. VCM is in the j cap direction, so VCM j cap. RCM and VCM put values you can put. Sin theta cos theta we know, just putting all those things we will get this thing. So that is a very complex thing, so but that is what the real thing is. So L orbital we are going to get this thing, and if I get the overall magnitude of this L orbital, so that is going to be this, and this L orbital is going to be along this direction perpendicular to this RCM. Obviously it has to be perpendicular to both RCM and VCM. So LCM about O would be like that, and it has a x and y component. Its x component would be somewhere here like this, and z component would be like that. Z component would be like that, and we can represent that. This is the net angular momentum of center mass about O, and that is the x component of that angular momentum, and that is the z component, and these are the values, and we'll use later also. Okay, so this part is done. Now the magnitude of angular momentum of the assembly about the center mass. So that's what I make this video for. So now let's try to locate the principal axis. So isn't it clearly looking that this is about this rod, this whole assembly is symmetric, and if I take a one axis like that, about this also the assembly is symmetric, and if I take this axis, so that is about this, the assembly is symmetric. So my principal axes are these are the x and y and z. So y and z are any two axes. This I have drawn through center mass imaginary discs parallel to these discs. So y and these axes I have labeled as a different because they are different than x, y, z. So I have labeled them x dash, y dash and z dash. X dash is along the axial rod, and y, z, z dash are pair of two perpendicular axes passing through the center mass and in the plane of that imaginary disk. So these are our principal axis. So first of all I'll try to find the moment of inertia. So moment of inertia about this x dash axis, and by symmetry about y dash and z dash should be same. So Ix dash this disk has a moment of inertia ma square by 2 and about this axis, and this disk has also moment of inertia 4m into 2a whole square by 2, add them to get 17 ma square by 2. And for the y dash or iz dash, we'll have to use the parallel axis theorem. So for this disk, first of all, suppose I am finding a moment of inertia about y dash. So first of all, find the moment of inertia about an axis that passed through its center mass and parallel to y dash, and that would be ma square by 4 like this, and plus this distance plus md square, and that distance would be m into this mass is m, this mass is 4m, so this center mass will divide them in the ratio of 4 to 1. So this distance will be 4l by 5 and that distance will be l by 5. So plus m into md square plus m into 4l by 5 whole square, and similarly for this thing like this, and then add them and simplify. So you are going to get I dash or iz dash, both are simple, that is a 469 by ma square by 20. See, you can see in the solution this was given as a one of the solution. Most of the solution have made this correct, and see, they have used the angular momentum or center mass just what is taught at the 11-12 level, that is ICM omega, and this Ix dash is taken and this omega is taken and this just multiply by that thing, they got this answer, and that is absolutely wrong answer. So these are the moment of inertia. And now further, now we want to find the component of the angular velocity along the principal axis. So see, the net angular velocity is omega net along negative x direction, and this angle was theta, This angle is theta. So along the principal axis, along this x dash axis, omega net will have a component omega x dash, and it will have a component along y dash, that is omega y dash, and it will not have any component along z dash axis. So omega x dash is omega cos theta, omega mean omega net obviously, and omega y dash is omega net sine theta, and omega z dash is 0. And omega net is omega cos theta, and just put these value, and we have all the cos theta sin theta values, so we are going to get omega dash, omega y dash, and omega z dash as shown. You can check calculation, but I strongly advise not to do, because all these calculation are very not good values, because this was not made in the right spread, right? They should have not taken care of all the values. Okay, so the method is important, but still I have got the correct values in the solution. So understanding is the method. Right thing is to understand the method. Okay, that we have got now that we have got omega x dash, omega y dash, omega z dash, and also I x dash, I y dash, I z dash. So like this. So then we will have we are looking to find the angular momentum of the center mass. So then we will have LCM. First of all, now that angular momentum would be called the spin angular momentum. There is nothing but the angular momentum of the center mass. So because there is no omega z dash, so it will not have a z component of the angular velocity. So LCM x dash would be along omega dash, LCM y dash would be along omega y dash, but net L will not be in the direction of omega, because these moment of inertia are not equal. If these moment of inertia would be equal, then the net L would be along the net omega, but that will not be the same. Alright, so LCM x dash is omega x dash, that was I explained. LCM y dash is IY dash, omega y dash. LCM z dash is IZ dash, omega z dash. And just put the values, these value, more cumbersome answer will come, but it will come. So this is what, so we've got this LCM, and now the magnitude of this angular momentum would be the square root of LCM x dash whole square plus LCM y dash whole square plus LCM z dash whole square, and if I get the square and then add and then a square root, so finally I will get something like 9.36 ma square omega. So again this option is also not correct. Alright, and then that is what that was as the magnitude of z component of L. So see, when we talk about the net angular momentum, L was given in the question, that was a net angular momentum. So net angular momentum is the sum of the spin angular momentum and orbital angular momentum. So this is L orbital, L spin. L orbital is the angular momentum of the center mass about O, and L spin is the angular momentum of the about the center mass. So that's what written, and this symbol I had given LCMO, and this symbol I had given LCM. So LCM, this is a LCM, this was LCM x dash, this is LCM y dash, this part I already have drawn. This is the angular momentum about center of mass. It has a x dash, it was along the principal axis, x dash and y dash. And LCMO, that was the angular momentum about angular momentum of the center mass about O, and it had both, it was in some negative x direction also and the z direction also, and that was like that. And we have calculated before, that was the LCM OX and that is LCM OZ, and the values we had written, all the values we had written, you can check. Okay, whatever. So the overall angular momentum Z component, so that would be obviously LCM OZ plus LCM y dash cos theta, and this will have a z component that will be minus LCM x dash sin theta. So z component of the angular momentum would be this LCM OZ plus LCM y dash cos theta minus LCM x dash sine theta, and just take all these values and put the value. Oh, you will get something like 78.63 ma square omega. So though this was a very flawed question, ideally it should not have come in the first place, but that it has come, that paved the way for all those IIT-JEE educators also, and also IIT-JEE aspirant, to go for how to approach for what is the right way to solve this question. The only right way to solve this question is the inertia tensor, and that is not in syllabus. So I have presented you a right way, and that is how it should be presented. So I hope you would have understand. If it is not clear, so I request you just go through again the inertia tensor part, and once you understand, that would be pretty easy. Thank you.